In the crucible of global conflict, a nation is defined not just by the courage of its soldiers, but by the might of its industry. During the Second World War, America undertook an industrial mobilization unlike anything the world had ever seen. At the heart of this effort was a seemingly impossible task: to build a bridge of steel across the ocean, a lifeline of ships to supply the forces of freedom. They called them Liberty ships. They were built faster than anyone thought possible, a symbol of American resolve. But these steel titans held a dark secret, an invisible flaw that turned triumph into terror. This is the story of that flaw, a story of catastrophic failures, a desperate engineering investigation, and a quiet, unexpected human triumph that would not only help win the war, but would change the way we build our world forever. This is an engineering detective story, the story of the ships that broke themselves.
To unravel this incredible story, our investigation will unfold in 3 parts. First, we'll establish the historical context. We'll journey back to the desperate days following Pearl Harbor to understand the immense pressure and the critical need for ships that gave birth to the Liberty program. We'll meet the industrial visionary Henry J. Kaiser, the man who promised to build ships faster than the enemy could sink them. Next, we'll confront the problem. We'll witness the shocking disaster of the SS Schenectady and uncover the epidemic of failures that spread fear among the very sailors who depended on these vessels. We'll follow the initial investigators as they chase down leads, only to find themselves at a dead end. And finally, we'll uncover the solution, a breakthrough that came not from a committee of experts, but from an unexpected hero on the factory floor. We will see how this discovery led to a revolutionary new way of building, the birth of the Victory ship, and a lasting engineering legacy that ensures the safety of structures we rely on to this day. Our story begins in a world at war.
December 7th, 1941. The attack on Pearl Harbor thrust a reluctant America into the heart of the Second World War. The nation was now fighting a war on 2 fronts, across the vast expanses of the Pacific and the treacherous waters of the Atlantic. This global conflict would be a war of logistics. Victory would belong not just to the bravest, but to the best supplied. The situation in the Atlantic was dire. German U-boats hunting in wolf packs were devastating Allied supply lines. For every new cargo ship launched, 2 were being sent to the bottom of the ocean. Britain, standing alone, was facing starvation. The lifeline of food, fuel, and munitions was being severed. Traditional shipbuilding was a craft of time and patience. A single vessel, its steel plates painstakingly riveted together, could take 8 months or more to complete. America did not have that kind of time. The demand was for 7,000 tons of supplies per ship, and thousands of ships to protect those supply lines and support the eventual invasion of Europe. As Winston Churchill would later state, the Battle of the Atlantic was the dominating factor all through the war. Never for one moment could we forget that everything happening elsewhere depended on its outcome. A new approach was needed. A miracle was required.
The man who answered the call was an outsider, an industrial titan named Henry J. Kaiser. He had built the Hoover and Grand Coulee dams. He had paved highways across the nation, but he had never built a ship. He was a visionary with no shipbuilding experience, and that was perhaps his greatest strength. He saw not tradition, but inefficiency. Kaiser's approach was revolutionary. He famously promised to do for ships what Ford did for cars.
He tossed aside the time-honored tradition of riveting and embraced a faster, more modern technology, welding. Instead of building a ship piece by piece on the ways, his shipyards would prefabricate massive sections, some weighing over 200 tons, and then weld these modules together. The results were staggering. Construction time plummeted from over 230 days to an average of just 42. At its peak, his Richmond shipyard was launching a new ship almost every other day. Kaiser's promise became a rallying cry. We're going to build ships faster than the enemy can sink them. We're going to build them by the hundreds, by the thousands, if necessary. He was making good on that promise.
The vessel at the heart of this miracle was the Liberty ship. It wasn't a beautiful ship, nor was it particularly fast with a top speed of just 11 knots. It was a workhorse. A simple, reliable design based on a British model. At over 440 feet long, it was capable of carrying nearly 11 tons of cargo, everything from tanks and planes to wheat and ammunition. Over the course of the war, 2,710 of these ships would be built, crewed by over 14,000 sailors. Each ship was an immense undertaking, composed of 250,000 individual parts. The key innovations were in its construction, a modular design with standardized interchangeable parts, and a hull that was entirely welded, not riveted. This welding was the secret to its rapid production. But hidden within its utilitarian design was a seemingly minor detail, a feature designed for efficiency that would prove to be a fatal flaw. Its square cargo hatches. Remember that detail. It will become critically important later in our story.
Kaiser's shipyards were cities unto themselves, operating 24 hours a day, 7 days a week. The production process was a finely tuned choreography of steel and manpower. Massive sections were prefabricated, then moved on conveyor systems to the slipways for final assembly and launch. The pace was relentless. Production records were shattered almost weekly. The SS Robert E. Peary was famously assembled in a mind-boggling 4 days and 15 hours. Across 7 major shipyards in the United States, a new ship was being completed, on average, every 42 hours. This incredible feat was made possible by a workforce of over 90,000 Americans. It was also a time of profound social change. With millions of men overseas, women entered the heavy industrial workforce in unprecedented numbers, becoming skilled welders and fabricators. The Rosie the Riveter campaign became a symbol of this national effort. Through intensive training programs and incentive systems, a new generation of shipbuilders was created, fueling the miracle of mass production.
Then, on January 16, 1943, the miracle began to unravel. The SS Schenectady, only 10 weeks old, sat quietly in the calm, cold waters of a Portland, Oregon harbor. There was no storm, no enemy action. Suddenly, a sound like a rifle shot cracked across the water. Within moments, before the eyes of stunned dock workers, the impossible happened. The Schenectady, a 500-foot vessel of solid steel, broke completely in two. The immediate impact was shock and panic. This was the first major structural failure of its kind. It sent a tremor of fear through the Maritime Commission and posed a direct threat to the entire war effort. If these new ships were unreliable, the bridge across the Atlantic could collapse. The initial questions were frantic and wide-ranging. Was it sabotage by German agents? Was it a fundamental design flaw in the original British blueprints?
Were the materials shoddy due to rushed production? Or was it bad welding from an inexperienced workforce? The investigation began immediately.
The Schenectady was not alone. Reports began pouring in from across the globe. The SS John P. Gaines split in two in the Pacific. The SS James Mackay fractured in the Atlantic. The SS Cape San Juan cracked while sailing in convoy. In total, over 20 ships would fracture completely. Hundreds more developed serious cracks. A terrifying pattern emerged. The failures were happening almost exclusively in the cold waters of the North Atlantic. Some ships simply vanished at sea without a distress signal, leaving behind only an oil slick and haunting questions. The impact on morale was devastating. Sailors began to fear their own ships. Merchant mariners, who already faced the constant threat of U-boats, grimly nicknamed the Liberty ships death traps. Confidence in America's industrial miracle was shattered. As one report noted, these weren't war casualties. These ships appeared to be committing suicide. An urgent response was required. A board of investigation was immediately formed. All ships were ordered for inspection, and as a temporary fix, crews began riveting steel crack arresters onto the decks of existing vessels, a desperate attempt to contain the mysterious force that was tearing their fleet apart. The Board of Investigation pursued every initial hypothesis with urgency. Sabotage was ruled out. The failures were too widespread and followed a distinct pattern that pointed not to malice, but to a problem with the ships themselves. Laboratory research began on an unprecedented scale. Over 200 steel samples from failed ships were analyzed. The results were baffling. The steel met all required specifications for strength and composition. The welds, when examined microscopically, were found to be technically perfect. The British designs had a proven track record, and reports showed the new workforce, including the thousands of women, were properly trained and highly skilled. Every logical avenue led to a dead end. It was then that investigators began to form a new hypothesis. The problem was not in the quality of the steel, but in its fundamental properties. A connection was made to the consistent reports of failures in cold water. They were witnessing a phenomenon engineers were only just beginning to understand: brittle fracture. The focus shifted from sabotage and bad welds to the esoteric world of physics and the ductile to brittle transition temperature of steel.
To understand what was happening, we must understand how steel behaves. Under normal conditions, steel experiences ductile failure. When stressed, it bends, stretches, and deforms before it breaks, giving clear warning signs. But at low temperatures, steel can undergo a frightening transformation. It loses its ductility and experiences brittle failure. It shatters suddenly, like glass, with no deformation and no warning. The critical threshold for this change is the ductile to brittle transition temperature. For the steel used in Liberty ships, this temperature was between 50 and 60 degrees Fahrenheit. The water of the North Atlantic, often between 28 and 40 degrees, pushed the steel deep into its brittle state. The consequences were catastrophic. In this brittle state, cracks could propagate at near the speed of sound. The stored energy in the hull was released explosively. A ship could break apart almost instantly, giving the crew no time to react. The key discovery was clear. Failures occurred exclusively in cold waters. Ships in warm climates remained intact. Temperature was the missing factor.
Brittle steel alone wasn't enough. It needed a starting point,
A trigger. That trigger was a design flaw, the sharp 90-degree corners of the cargo hatches. Engineers know that sharp corners are stress concentrators. As the hull of a ship flexes with the motion of the waves, the forces flowing through the steel pile up at these sharp corners. It's similar to bending a paperclip back and forth at the same point. Stress at these corners was measured to be 3 to 4 times higher than anywhere else on the deck. Each wave was an additional load on these critical points. This created the perfect storm of factors. First, the welded hull provided a monolithic, continuous path for a crack to travel. Second, the cold water made the steel brittle. And third, the sharp corners acted as stress concentrators, initiating the microcracks. Once a crack started, the brittle welded hull offered no resistance. The fracture would propagate at near sound speed, and the ship was doomed.
This led to a difficult paradox. Welding was the key innovation that allowed for the speed of mass production, yet that same feature, the continuous monolithic structure, is what created the vulnerability. A traditional riveted hull was like a patchwork of plates. Each plate was a separate piece, and the riveted seams acted as natural crack arresters. If a crack formed, it would stop at the boundary of a plate. It was a proven, reliable, but slow technology. A welded hull, by contrast, was a highway for cracks. It had no natural barriers. The technology was so new that its limitations, especially concerning residual stress concentrations from the welding process itself, were not fully understood. Traditional knowledge didn't apply. The very innovation that enabled the production miracle was also its greatest weakness. A solution had to be found that preserved the speed of welding while eliminating its fatal flaw.
The final piece of the engineering puzzle came from the most unexpected of sources. Not a lead engineer, but a welder on the graveyard shift at Richmond Yard No. 3 named Bessie Hamill. Having worked for 8 months, she had developed an intuitive understanding of steel. She observed that the official welding procedure, welding from the edges of a plate towards the center, caused the massive steel plates to deform as they cooled. She knew with the certainty of someone who works with her hands that this was wrong. You don't build something by trapping forces inside of it. On her own time, she conducted independent experiments on scrap steel. She developed a new sequence, welding from the center outwards in an alternating pattern. Her test plates remained perfectly flat without distortion. She had discovered that the established procedure was locking immense residual stress into the very fabric of the ships. At great personal risk to her job, she broke the chain of command and presented her findings. She had found the key to solving the Liberty ship failures, and in doing so, laid the foundation for the Victory ship design.
The scientific principle behind Bessie Hamill's discovery was simple, yet profound. Heat causes expansion, and cooling causes contraction. The original method, welding from the edges to the center, trapped this contraction, causing the outer edges to pull inward, locking stress into the structure and distorting the plates. Bessie's new method, welding from the center to the edges, allowed the steel to expand and contract freely toward the open, unwelded edges. Stress dissipated instead of being trapped. An alternating pattern balanced the thermal forces, ensuring the plates remained flat and true. The implementation challenges were enormous. It meant breaking established procedures, retraining 90,000 workers, and overcoming skepticism from engineers who were reluctant to accept that their calculations had missed a critical real-world factor. But the evidence was irrefutable. The welder from the graveyard shift had been right. The science was sound. The gamble had paid off.
The solution was not just to patch the old ships, but to build a new one. The Victory ship was the successor to the Liberty, born from the lessons of catastrophic failure. The contrast was night and day. Where over 20 Liberty ships broke apart, the Victory ships suffered 0 catastrophic failures. This was achieved through a complete restructuring of the production process. The ship was divided into separate smaller modules. A new improved steel with manganese was used. The sharp cargo hatch corners were rounded. And most importantly, all welding followed Bessey's center-out method. The result was a ship that was not only safer, but faster and stronger, serving for decades after the war. The crisis had been transformed into a revolutionary leap forward in shipbuilding. The Victory ship pioneered a truly modern form of modular construction. Sections like the bow, cargo holds, and engine room were prefabricated separately. Each module was built in a controlled environment where specialized welding teams could ensure perfect quality control and adherence to the new complex welding sequences. Crucially, after fabrication, these modules were heated to 1100 degrees Fahrenheit in massive ovens, held at temperature for several hours, and then subjected to a slow, controlled cooling. This process, known as post-weld heat treatment or annealing, relieved the internal stresses locked in during welding. The revolutionary results were immediate. Inspections found 0 stress cracks. The new ships were 20% stronger than the Liberty ships, and after the initial setup period, construction was actually 50% faster. This system, modular fabrication combined with strict quality control and stress relief, became the foundation for modern shipbuilding. The final comparison tells the whole story. While a Liberty ship took 30 to 70 days to build, a Victory ship took just 18 to 30. They were faster, at 15 to 17 knots compared to 11. They used a superior killed steel, had rounded hatch corners, and utilized the center-to-edge welding method with post-weld heat treatment. The service history is the ultimate verdict. Of the 2,710 Liberty ships built, over 20 were lost to structural failure. Of the 534 Victory ships built, 0 were lost. The reliability improvement was 100%. This achievement eliminated the brittle fracture problem, created safer conditions for crews, and established new industry standards that validated Bessie Hamel's methods. The wartime impact was decisive. Victory ships carried over 8,000 tons of cargo each, ensuring a faster, more reliable delivery of supplies to the front lines. They enhanced Allied logistics capabilities and directly contributed to victory in both Europe and the Pacific. What began as a story of disaster ended as a story of ingenuity and triumph, a legacy of safety and innovation that endures to this day.